Okay, so good morning, and so we start something new, and this is about the specific heat of solids, and this is not going to be like multiple lectures; just a couple will be sufficient. So we start with some basic facts. Okay, so let's think of something like metallic solids. Okay, so you can think of them as a collection of ions on a lattice. And you will learn about different kinds of lattices, etc. But there'll be some periodic structure, so which is just some periodic structure. Okay, and and there will be a free. I'll put free in quotes. Free gas of valence electrons. Okay, so something like sodium metal. Okay, this if it would consist of Na plus single plus ions, and there's one valence electron. Hopefully you remember your chemistry. Per sodium atom. Okay, so this is the rough scenario, and so so it's known that the specific heat at low temperatures goes as follows. Goes as so C goes as some AT plus B T cubed, where A and B are constants. Okay, and so there are these two contributions. At high temperatures, we will discuss it later, but at low temperatures, this is the key thing. And this term comes from the electron gas, and this comes from the ions. Okay, so what we will do in this course is that we will derive both these things, but what we will do is we'll do it in two parts. So the first part will be where we'll focus on the ionic contributions, and the second part will be on the electron gas. But the second part will require us to develop some technology, which we will develop after we're done with this, and then it will be an exercise in straight ahead statistical mechanics with the new ideas that we learn to compute, show that the electron gas will give a term which goes, which will give a specific heat which goes as T. Okay, so this is the general setup. So are there any questions or comments? Okay, so what we will do today, and maybe tomorrow, we will determine the specific heat This is our target. Okay. And the nice thing is that we don't need too many new ideas. We just have to, do the standard thing, compute the canonical partition function, from that compute the internal energy and take a derivative with respect to time, temperature, and then you get the specific heat. And then you start taking limits. Okay. So this is what we'll be doing. And so what we do is we will begin with a simple model. Okay. That actually does okay at high temperatures. But doesn't get the low temperature behavior. This model this is called the Einstein model. Okay, then we'll fix it. We will then look at an improvement, improved or different model. That gets the low temperature behavior also correct. And this is the Debye model. Okay, so the plan is to work through the Einstein model and the Debye model. Okay, so this is what we want to do. So before we do that, let's. So what we will do is, what is our system? Say n ions on a three-dimensional lattice. Okay, and in contact with the heat path. Okay, so this is what we have. And so what we want to do is we need a little bit more substance. So let's go back to classical mechanics. So this system has how many degrees of freedom? We're doing classical mechanics. Yeah. So there are 3 n degrees of freedom, and at equilibrium, and the lattice points, or the points on the lattice, okay, so the points on the lattice, they are the equilibrium positions. Okay, so nothing deep in this thing. But once it's in contact with temperature, you start getting fluctuations because energy of the ions so they will start fluctuating at finite temperature. Okay, at finite temperature, the ions can oscillate about the equilibrium positions. That we know. Okay, so if you remember your classical mechanics course, we studied this kind of problem where we had a system which was at equilibrium, and then we studied what we call small oscillations, right? So this is what we did, and from your classical mechanics course, we learned about small oscillations. Okay, and then in that you sort of got normal modes. These words should come to your, should remind you with something called normal frequencies. Okay, so and there would be, so because this whole system, if I translate, there would be 1 0 mode. Okay, and then omega 2, omega 3, so on and so forth. There would be a spectrum of 3n frequencies. Okay, so this is what you would have learned. Okay, so this 0 is because there's always one overall translational mode. Okay, so but this will require small oscillations, and so these frequencies are associated with those small oscillations. Okay, so does anybody remember, have questions about this point? I mean, this is something which you will learn in classical mechanics, and there are some of you have probably haven't done this, but it doesn't matter. What it says is that there are, if you try to do fluctuations, there'll be collective excitations, which are the normal modes. So it's not like you jiggle only one atom, one ion. It'll be, a collective. There can be several things which will move in the thing. So these will be normal modes, and there will be as many normal frequencies as there are degrees of freedom. So there'll be 3n such things. And 0, I'm just writing. You can call it omega 1 if you want. Why is it 0? It's a simple thing, but we will. Is this okay? Hello? Okay, good. So now we are, so this is the background, but the Einstein model, now we will discuss the Einstein model. Okay. So it says that, we treat the ions as 3n oscillators with the same angular frequency omega. Okay, this is obviously in contradiction with this statement here, but it doesn't matter. We want to do some model, and so we just say that it has a single frequency omega. Okay, and so now let us. So this is so we need to compute the canonical partition function. Okay. So Z, capital Z, that is the symbol for this, we'll write it as little z power 3n. Okay, so we are acting like there are these 3n oscillators, and of each of frequency omega, and so we just say that little z, and what should little z be? Not equal to, what is it? Anybody? No, just, no, that is the details, but what is little z? That's all I'm asking in words. Exactly. other person was just saying that thing in words. So, okay. So from quantum mechanics, we know that the energy of a harmonic oscillator is something like this. Okay. And what does n take values? N goes from 0, 1, 2, 3, so on. Okay. So Z will be summation n equal to 0 to infinity e power minus beta in times this energy, so it's just n plus half h cross omega. Okay, so what I'll do is I'll pull out this beta h cross omega by 2 outside. Okay, and this is a geometric series, and as long as and the object which is summed over is modulus is less than 1, so it's convergent. You can just write this. So okay, hopefully you remember this. So x should be just e power minus. Okay, so what I'll do is I'll just simplify it further. I'll multiply numerator and denominator by e power plus beta h cross omega by 2, so that I'll get something like this. This is just a 2 times sine hyperbolic beta h cross omega by 2. Okay, so this is the computation of little z. You can see it's just the world's simplest computation. We just put that in and do a geometric series and sum it, and then I'm just simplifying it. Okay, are there any questions with regard to this computation? Okay, so we get our final result. Okay, we have computed. This is little z, and it is little z power 3. So that's all. Okay, so now what we want to do is, what is the internal energy? There are many formulae, but this is the simplest one. But we can also write this as 3n times 1 by little z okay, and little z was inverse. Okay, so let's just do that, and we get 3n into 1 by z will be remain here. Okay, so now there are two minuses, so the plus, it becomes plus times beta is h cross omega. Okay, so that's what we get. And so you can see this z will cancel this one of these guys, and so we'll get 3n I forgot a 2 somewhere. Yeah, just 2. Okay, so it will be 3n h cross omega times cos over sin, which is cot hyperbolic. Okay, I think I got it right. All the factors of 2 are okay, I think. Oh no, there's a 2 here, there's a 2 here, there's a 2 here. So I think there's another 2. Okay. So let us plot this. So first thing is, before we do anything, let's ask how the cot hyperbolic x behaves for large x. Can someone tell me what happens when a cot hyperbolic of x, as x is very, very large? Anybody? Yeah. The other limit? So tan hyperbolic of x goes as x. So this will go, it will blow up. Yeah, but it goes as 1 by x. To infinity, so as x goes to 0. Okay, so we keep the dominant piece. I don't want to write it. Yeah, because it's cot hyperbolic. It goes like 1 by x. Okay, so from this we can work out certain limits. So the point is, so x being very, very large is beta being large compared to h bar omega, and so that is low temperature. So this will be low temperature. And this will be high temperature. Okay. Is this okay? Okay. So let's check the high temperature answer. So at high temperature, you just replace this by U, which is T tending to infinity or T very large, and or beta tending to 0. Okay, U goes to 3n 1 by x, which is 2 by beta h cross. Okay, and U goes to 3n h bar. Okay, because it goes to 1. Okay, so now first let us look at the low temperature. What does this mean? At 0 temperature, what do you expect? So I want you to interpret this answer. If you have an oscillator, what is its? Yeah, all oscillators are in the ground state, and each of them has a ground state energy of half h cross omega by 2. So this makes sense. Okay, and so this is what we get, and so this is, and one more thing you can see is that from this you will see that C will tend to 0, and this will tell you that C will tend to some constant 3 n kb. Okay, so at high temperature, and so there's a law. This actually agrees with an experimental observation with something called Dulong and Petit. Okay, and C going to 0 also agrees because AT cubed, BT cubed, T going to 0, it goes to 0, but we have to see how it goes to 0. Okay, C tending to 0, this is the correct value at T equal to 0, but we have to, but not quite correct, not correct approach, as we will see. Okay, so for that we have to compute the specific heat properly. C is just D. U was some cot function, right? What is it? 3n h cross omega by 2. Cot hyperbolic beta h cross omega by 2. Okay, so we can write this as 3n h cross omega by 2 into d by d beta of cot hyperbolic beta h cross omega by 2 times d beta by chain rule. Okay, so now question to you is, what is d by dx of anybody? Does anybody know this? Okay, I think there might be a sign. Okay, I will leave it to check for it. Check. I'll let you check that. And I'll fix the sign by requiring something sensible. I want C to be positive, right? So I will do that. Okay, so let's do that. And and let me just do one more computation. D by d beta is 1 by kb into minus 1 by t square. Okay. Yeah. Thank you. Thank you very much. Yeah. Okay. Okay. So this I can write by as kb by kb beta square. With a minus sign. Okay. So we'll put all these things together and get C equal to 3n h cross omega by 2 into, so there is one minus sign coming from this here, and there's also minus sign here. These two cancel, so I don't need to worry about signs anymore. Times cosecant, which I can write as 1 by sin. Let me write it as inverse of that. Okay, times d by d beta, this thing, so into h cross omega by 2 times kb into beta square. So let's just collect things together. So this will become, so that's a 3n, of course, that will be there. But now there's a h cross omega by 2, h cross omega by 2, I can take it inside. I also have a beta square, I can do that thing. So I'll get 3n kb into, so beta okay. Is this clear? By some fluke, I don't have some errors. I think it's it's correct. Okay, so now we'll do some plots. Okay, so the first plot I want to do is U versus T. Ah, why? We have to go back here, right? So we saw some limits. So we saw that U went to 3n kb t, which is U versus T would be a straight line with slope 3n kb. So okay. So this is that straight line, but I just want to draw now. Okay, so it will be something which will look like this. Okay, so the white line is this thing, and this is just a straight line. What was the slope? 3n kb. Okay, this is what we get. Is this fine? Okay, so now what I want to do next is to plot and let's do C by n. Okay, I should have even that there versus T. Okay, and then let's draw some asymptotics. Okay, so this is 3 kb. Okay, so one thing which we need to do, so that's we check that, but for low temperature behavior, we need to look at this at low temperature. Okay, so at low temperature, okay, that is beta tends to infinity. Okay, so and let's say that x will define not x, xi or zeta to be. Okay, so this is xi by this thing. So this thing goes as psi square, and sin h something will go as e power minus, where xi is this quantity. Okay. So c goes like this. Okay, so it falls. So this is not power law. This falls exponentially to 0. It's faster than any power law, right? Exponentially, because xi is going, beta goes to infinity, xi is going to infinity. So e power minus infinity goes to 0. Okay, so that's what will happen. And so this curve will look, it will asymptote to 3 kb, that's for sure. But this behavior, it will be very, very sharp like this, asymptote to this. So this is the thing. And this behavior is, if you wish, okay, so it goes to this thing, but not correct. This behavior is not correct. And Okay, so this is the problem, but it definitely reproduces. This is this line is too long for theta. So this is a good point for me to pause and I open the floor for questions or comments. Are there any comments or questions? Is everything clear? I mean, so once you define the model, the computations are straightforward. So, but I would request you to plot these actual functions. These functions are not so hard to plot. Plot them directly on using some plotting package. Okay. So I just so I since there is silence, but I'm assuming my connection is still there. So there are just two scales in the problem. Okay, so energy scales. One is kBt and the other is h cross omega. Okay. So what is small t here is saying kBt, the dimensionless parameter h cross omega is much less than 1. Okay. And what is large t? The same quantity. Okay, so, and if you look carefully, everything came in these combinations, right? So every time the exponential of xi, okay, so this was up to a factor of 2, this is just that zeta. Is it zeta or xi? No, this is xi. Slash xi in latex. Okay, so it's xi. Zeta looks like this. Yeah, actually, there are some online things which let you practice how to write Greek letters and shows you which way to go. Please, if you have some time, take a look at that. Okay, so that sort of concludes our attempt at the at giving the ionic contribution to the specific heat of solids, and that doesn't seem to work too well at low temperatures. At high temperatures, it's consistent with the experiment, so it's not a total disaster. So the Debye model, okay, which we will study tomorrow, which we will study tomorrow, rather next lecture. Will fix this issue. Okay, but there is a beautiful idea underlying which will even looking at these this particular problem that we have done is about it goes by the idea of second quantization, which I want to discuss. Okay, so I mean what it says is that so suppose we have something which goes like whose energy goes like this, E times M into H cross omega. Okay, so which I'll also write it like this, where I'll define epsilon to be H cross omega. Okay, so consider n particles, each with energy epsilon. The total energy as I wrote above. So maybe I don't even need this formula here. So okay, so that's the total energy. This but now the whole point here is that we have multi. So this is a system with multiple particles. Okay, with n counting the number. Okay, but up to, if you look at this, you compare with the SHO spectrum, which is E equal to NH cross omega plus 0 point energy. So if we just ignore 0 point energy for a moment, it looks like this. But in the simple harmonics oscillator spectrum, N is not particle number or something. It's just the level of the state. So what will happen is that so here are two systems which are distinct, but they look the same. If you in terms of statistical mechanics, okay, if you're doing this computation, what it's saying is that so if you go back and we look at our little z computation, okay, so let's compute little z. Okay, so here this would be summation n equal to 0 so let me write something. Consider okay, so what does this look like? This looks like a partition function where the system could have okay, this looks like the partition function partition function of a system where particle number is not conserved. So we can annihilate particles left, right, and center. So each term in this summation tells you the contribution of n particles. So for n counts how many particles are there. But up to some 0 point energy, this Z looks exactly like that of the simple harmonic oscillator. Okay, so the second quantization picture is this story. Okay, so but algebraically it is the same. So there's some a dagger you can write. So if you remember, there was some a dagger commutator. There was this algebraic formulation, and the nth state was something like this, right? It was a dagger power n. Probably I don't remember this. Probably it's n factorial. So acting on this. Okay, so now a dagger creates a particle. Okay, interpretation is totally different from simple harmonic oscillator. And what will A do? Annihilates, or destroys a particle. And the Fonda relation A of 0 equal to 0 says that you cannot remove any more particles, can't annihilate any more particles. Okay, so this is the second quantized picture. Only thing common with the simple harmonic oscillator is the commutation relations here. But the interpretation, so A is not some, x plus IP. By some x naught and some p naught. It's not arising from this. Okay, so it's just formal similarity with that. And so this is the second quantized story. And so the quantization, the correct quantization of ions on a lattice. Okay. So this would be quantum mechanics of particles on a periodic potential, says that the normal modes that we computed in ZM are associated with what we'll call quasi-particles called phonons. Okay. So it's like take on like for bosons. Okay. And there are 3n different phonons with energies, whatever we wrote, right? H cross times. Yeah. Mm-hmm. No particles. There are no particles. The vacuum has no particles. The, yeah, but that's not so important. That's some constant shift of the energy of the ground state. I can always choose. Okay, naively. I mean, let's just. So that's not going to complicate many things. Okay, so we could associate energy half h cross omega to ground state, but at the end of the day, that will give you some constant factor. It will be some constant number. That's okay. Okay. So the question is, what is the vacuum energy, which I can shift always. I can do a shift and get it away. But when if you couple to gravity and other complicated systems, you can't. You don't have that freedom to shift. Okay, so that energy has a different meaning. So, but for my purposes, it's good enough. Is that clear? Hello. Okay. So there are 3n different phonons, and so now this. So the point here is that you pick a particular. So if you have a phonon of a particular frequency, then you know that you can have one phonon, two phonon, etc. So then you need to ask what is the average number. So if you pick a frequency at temperature T, how many phonons will be there on an average? Okay, we'll answer this question. Okay, so it's the analog of saying which excited state a simple harmonic would be, oscillator would be in, but here that's not the thing. Okay, and so we will discuss how to handle cases where multiple like total numbers are not this thing. So, but we'll do a cheap method now, and probably 2 lectures later we'll do something much more sophisticated. Okay, so this is what we have, but in general, it is hard to determine the spectrum, right? Spectrum of normal frequencies. Okay, so but what we can do is we can define something called rho of omega, d omega. This will just tell you number of normal modes that lie in the interval omega to omega plus t. Okay, so because 3n can be very, very large, I will get to a number, so it's better to think of some continuum way of doing it. Okay, and so this is one thing. So how do we determine rho of omega? at temperature T, what is the average number at a fixed frequency. Just call this n of omega. So again, n of omega d omega would be probably the number of guys in the thing. But anyway, you understand what I'm saying. So if you can do all these things, okay. So the Debye model addresses this in some detail. Okay. And this is what we will do next lecture. So I'll stop here and pause for question. So are there any questions?